Welcome to lesson 22. So we're going to talk about parameter estimation. What that means is a lot of times in a population there is a value that we're interested in, maybe a mean or a proportion for that population, and we like to try to estimate it using sample data. So we're going to define the point estimate, we're going to talk a little about variability, and just briefly introduce the confidence interval, although we'll talk a lot more about confidence intervals with examples in lesson 23. So confidence intervals. So the big reason behind confidence intervals is if you just guess with a point estimate, so let's say I want to estimate the average height of all OSU students, and I guess a single value. So I guess 68 inches. Well, it's either exactly right or exactly wrong, right? It's not going to be, there's not much wiggle room there. A confidence interval introduces a range. So, I think it's, between, 54 and 68 inches. I don't know. That way, you're much more likely to be accurate. You're much more likely to have the mean in that range than just a single value. So it provides a range of values along with a certain degree of uncertainty. So it's not guaranteed to be in that range of values, but it's very likely that it is. So what we talk about estimation, so a point estimate is our single best guess. So if I wanted to guess the average height of all OSU students, and I took a sample of OSU students, the average from that sample would be my best guess. My sample mean from the sample. So it's whatever you actually saw in the sample. That's your starting point. And we usually want to use a sample statistic that is unbiased and has a small standard error. So what that means is, on average, we want it to be accurate for predicting the mean, and we don't want it to fluctuate a lot from sample to sample. So if we have a population and we want to know, hey, what is theta or what is mu, more likely in this class, take a random sample. Once you have that sample, calculate x bar or theta hat here, and then make your inference back to the population. So make your statement, tie it back in. So our happy place is when a point estimate is unbiased. Because if it's unbiased, this means on average, the sample mean is equal to the population mean, which is good, right? Because you want something that's going to be accurate over time. So in general, like if you're looking at unestimated, p hat is unbiased for p, x bar is unbiased for mu. So we really like those particular estimators. So the big idea here, the sampling distribution gives us an idea of how much x bar fluctuates from sample to sample, and it can tell us how close to mu we think it's likely to be. So the structure that we're going to use for confidence intervals in this class is going to be some point estimate. So usually this is x bar or p hat. Until week 10, it's going to be x bar. And then plus or minus some margin of error. So everything after the plus or minus, that's your margin of error. So you have to start first with your point estimate. So this is where your sample data come into play. So if you want to estimate the mean of a population, you're going to start, your starting place will be the mean from a sample. You want the population proportion, your starting off place is going to be your proportion from a sample. Standard deviation for your population, you're going to start off with the standard deviation from the sample. Although note, sigma, S is biased for sigma. It's not an unbiased estimator. So here, there are three main conditions that we're going to, so we're using like Z methods or Z procedures. They're the same thing. And in order to use it, we need to meet these three conditions. So the first, you need to ask yourself, hey, do we have a random or representative sample? You want to know that what's going on in this sample represents the population. If you can say yes, good. Then the second is going to be, is the sample size big enough that we know that the central limit theorem is going to kick in for the sampling distribution of X bar? So that kind of goes to, maybe look at the sample. If it's really skewed, you might need a bigger sample. If it's roughly symmetric, at least 12. But if it's really, really normally distributed, that population, you absolutely can just have any sample size there. And then the big one for at least this week and next week is knowing the population standard deviation, sigma. This is a little less likely in real life, but for these Z methods, when we calculate a Z score and use a Z table, this condition is really important. So some of the reasoning behind our confidence interval here. So here's an example. I am doing, comes from it's a calculator command. You don't need to worry about running it. But what I did is I decided to take a random sample of 16 observations from a population that's normal. It has a mean mu, but we don't know what it is, or I do, but y'all don't know what it is. The standard deviation is known to be 20, and I took 16 of them. So right now, I know the true value of mu. So looking here, the mean observed in our sample of 16. So when I took 16, our average was 236.96. So we're going to use this as a starting point to try and estimate what mu is. And then I'll reveal at the end, hey, do we know what here's what mu is. Did we get it in our interval or not? So our sample mean, it's that 236.96. So our best guess is going to be somewhere near there. But we need to figure out how near, how close. So starting off, we need to know about the distribution, the sampling distribution of X bar. So we already know a few things. We know that sampling distribution is normal because the population is normal. So we know how it's going to be shaped. We know how it's spread here. We know sigma of X bar is just that sigma of the population over 20, square root of our sample size. So sigma of X is 20 over the square root of our sample size is 16. Oh look, isn't that nice? So 20 over 4 is 5. So that right there, that's our standard deviation for sampling distribution. And then here's the thing we don't know. That center, it's centered wherever the population mean is, but we're not really sure exactly where it is. Oops. So even though we don't exactly know it, we do know that roughly 95% of all possible X bars, so all possible sample means I could get from samples of 16 from this population, are within roughly 2 standard deviations of mu. So this is coming from that 68, 95, 99.7 rule. That's where that 2 is coming from. So the idea is the sample mean that we observed one of these 95%? Because if it is, we can use that logic that, hey, if our X bar is within 2 standard deviations of the mean, that means the mean is within 2 standard deviations of our sample standard deviation. So it's kind of like the idea A is as far from B as B is from A. So if our x bar is within 2 standard deviations of mu, u is within 2 standard deviations of x bar. So 95% of the time that we take a random sample of 16, this is going to work. We're going to make an interval that will actually have mu in it. So our confidence is actually in the process of making the interval, not any particular interval, but this procedure of going plus or minus 2 standard deviations. That works about 95% of the time that you take a random sample. So returning to our example here. So my sample size is 16. We got 236.96 as standard deviation of 20. And then this was just filling this out again. So 20 divided by the square root of 16 ended up getting 5. So we want to figure out what is 2 standard deviations to either side. So this plus or minus, it means that, here, we'll show you. So 236.96 plus or minus 2 times 5. Well, that's nice, right? So I'm going to get 236.96 plus or minus 10. So that means you have to break it up. 236.96 minus 10, 236.96 plus 10. So I'll get, what, 226.96, and then equals 246.96. So my interval, I'm putting it here in interval notation, so parentheses, my lower one, so the one that's lower, the one that used subtraction, 226.96, and then comma, and then the bigger one, so 246.96, and then parentheses. Notice that 236.96 should be smack in the middle of those two numbers, like exactly in the middle. So here's our confidence interval here. So we can say we are approximately 95% confident that the true population mu is somewhere between 226.96 and 236.96. So then, here's the big reveal. Mu is equal to 240. So 240 is in the interval. This is good news. We're happy, right? We wanted to have an interval that had the true mean in it. I knew what it was. So this is good news. That is what you want. If you calculate a confidence interval, you want to have, one of those 95% random samples you could have gotten that leads you to an interval that has that true mean in it. Because you want to estimate the mean, so you want to estimate it accurately. So there is some variability, right? You probably noticed from sample to sample, the sample mean changes up. So if I take a sample of 100 students and take their exam scores, and then I take a new sample of 100 students and take their exam scores, they're not exactly the same scores, and they're usually not exactly the same average from sample to sample. So the point estimate is, it's pretty exact in the sense that it's just one value. So we would rather use a range of values. So a confidence interval, it can really increase the likelihood that our estimate is accurate. Because if you guess with just a point estimate, it's more likely to be wrong than it is to be right. So, like if you said, hey, I think the average height is 58 inches. Well, if it's 58.2, you're wrong. That kind of idea. So definitely it provides, like a range of plausible values. So these are values that, yes, we think, this would be a likely or, understandable value for the mean. So when we want to construct it, we start with our point estimate. So this comes from the sample. And then times a critical value. So for most of the rest of the term, it's going to be a z star. And times a standard error. And so for at least this week and next week, we're going to be using sigma of x bar. And then remember this entire thing. So the critical value times the standard error, that's our margin of error. Everything after the plus or minus sign is the margin of error. So we have our lower bound. Our point estimate is smack in the middle. The distance from the point estimate to the lower bound is just our margin of error. If you go the other direction, same distance as your margin of error goes to your upper bound. And that will be our interval. So the standard error is a measurement for how much the sample statistic varies from sample to sample. So if I take a sample of 100 and I take the average from that 100, and then I take another 100 and take the average from that 100, from sample to sample, how much is the sample mean varying from sample to sample? And absolutely, it's usually going to be associated somewhat with the sample size. In general, if your sample size is really large, your standard error becomes very small, which is good, right? Because it becomes a narrower interval that way. So, we're not going to expect you, for a confidence interval, and yes, this is some very technical way to phrase it, the critical value is going to be the z-score associated with and you could say alpha over 2, and the 1 minus alpha over 2 percentile, which is real goofy. And alpha is an error rate for this interval. So if I have a 95% confidence interval, that means, hey, 95% of the time I take a random sample, this works. Alpha would equal 0.05. So that would mean 5% of the time I do this, it doesn't work. That kind of idea. I'm going to talk about specific critical values. This one's a little goofy to word like this. So specifically, when we are looking at a 95% confidence interval, we're going to use 1.96. So in that last problem, we used that approximate, like the 68, 95, 99.7 rule to do 2. If we use the exact z-score, it's more like 1.96. So, let me see. The idea is if you have your point estimate within 1.96 standard errors, then so this could be x bar. So x bar plus or minus 1.96 times your standard error. Sorry, I'm running out of space here. We'll capture the parameter. So here are an example of several different ones. So here, this is my first interval. So here's my point estimate, and here is my upper and lower bound. This line represents that true parameter. So the first one, it contains that true mean. The second one, look, it crosses there. Yes, good. And you can keep looking, and all the way here's an interval that missed. What this means is this is a confidence interval that was made that doesn't have that true parameter, so it doesn't have the true mean for the population contained inside of it. And this is just to show that not all of them do. If it's a 95% confidence interval, roughly 95% of them will have the true mean. But if it's a 95% confidence interval, that also means that about 5% of them will miss. So we can be 95% confident the parameter is captured by this interval estimate. So it's not necessarily confidence in one particular interval, but it's confidence in this interval making process. This process works 95% of the time. And like we were saying, however, if it works 95% of the time, that means that it doesn't work about 5% of the time. So hopefully the sample that we took was a good sample and it's one of the 95% that works. But in real life, we usually don't have any way of knowing for sure. So our confidence here. So we start with that question, hey, what is theta or mu? Take a repeatedly random sample and then collect your sample statistics from each of those. You'll come up with a sampling distribution for theta, theta hat, or x bar. And then you can calculate all these different, so every time you collect a new sample, you can get a new confidence interval. So it's not like there's one unique confidence interval, it's based completely on this sample. So if you took a new sample, you'd get a new confidence interval. So if you have a 90% confidence interval calculated from every single random sample that you could possibly get from a population, that means roughly 90% of those confidence intervals will have the real mean in them. But that does mean that about 10% of them will miss. They won't have that true mean from the population in it. So what I wanted to describe here, the critical values, the phrasing was a little weird there. So if I want a 95% confidence interval, this means alpha is 0.05. If I add these together, it's 1. So the critical values are, so if I put 0.05 here, I'm going to get, well, the 2.5th percentile and the 97.5th percentile. Sorry, I didn't move over my decimals there. So here, I want the middle 95%. So if I want the middle 95%, oops. So 0.95. So I have the middle 95% here. Then you need to consider, okay, well, how much do I have left over? So if I have 95 inside, that means I have 0.05 left over. Now I have to split them into the tails. So 0.05 divided by 2, that means I have, 2.5% in each tail. And you can quickly double check 0.025 plus 0.95 plus 0.025 should add to 1. So here, the z-score here, this is the 2.5th percentile. Oh, I can't. Percentile. Because 2.5% are left on that side. Obviously, not really drawn exactly to scale. Versus if I look here, I have everything this way. So I have 2.5% plus 95%. That becomes my 97.5th percentile. And so our critical values are going to be the z-scores that go with this. So 1.96 or negative 1.96. So 90% confidence interval, that's your, you want the middle 90% of the data. So 90%, that means I have 10% left over. So if I split those in each tail, so that'll be 10 divided by 2, it's 0.05. 10 divided by 2 is 0.05. So I have 5% in my lower tail, 90% in the middle, and then 5% in my upper tail. Adds to 1. But here, that means I want my 5th percentile, and then 5 plus 90, my 95th percentile. And then 99 is going to be pretty much doing the same things here. Obviously, for me, it's not drawn to scale, so I have my 99% in the middle, which means I have 1% left over. So I have to split it in between each tail. So 0.01 divided by 2 is 0.005. Same over here. 0.01 divided by 2, 0.005. So this one, if you move the decimal over 2 places, it's like the 0.5th or the half of 1th percentile. It's a little funkier. Versus like over here, 99 plus this half percentile. This is the 99.5th percentile. And we'll talk about like the Z critical values. They're going to be the same values for this. You're not going to have to calculate this. I'm just trying to visualize like, hey, where did these critical values come from? So for 99% confidence interval, you'll use the Z critical value that's associated with the 0.5th percentile or the 99.5th percentile. It doesn't really matter which one you use. One's positive, one's negative. Okay, so now we're going to go into the intro to confidence intervals. So we're going to have a couple of examples, and we're going to finish up calculating sample sizes. So we'll see you for lesson 23.